We have selected 1850 megahertz as the operating frequency. The operating frequency is output from this connector. A 20 dB pad is mounted in series with the transmitter. So actually 90 dB microvolt is what is available at this point. A jointer cable is used because we are using the up converted frequency range of the instrument. The instrument is normally kept in CW mode, because CW mode is what is being used to perform the experiments most of the times. Any modulation is not being applied as of now. The control of the instruments can be studied by observing the videos of ATS20 in detail. The antenna can be rotated in manual steps of 1 degree, 5 degree or 10 degree or 45 degree by opening the menu of the stepper motor controller. We're normally going to use the slow mode of operation because this is a very heavy antenna and this will remove any jerks in the operation. For automatic rotation, the instrument will be put in the auto mode and the antenna can be rotated automatically. The receiver is again, by using the down converter, we're using the Teflon cable with the connectors which is being mounted to the down converter input, and a jointer cable is being used because right now we're using the down converter as the main input for the instrument. As we can see, to begin the experiment, we will first of all try to find out the behavior of these reference antennas. We're going to use the separation between the antennas as roughly about 2 meters, because the 2d square by lambda, the Fresnel distance for this particular antenna, since it is a huge antenna with a diagonal length of roughly 40 centimeters, so 2d square by lambda at 1850 megahertz would necessitate a distance of roughly about 2 meters right now. Now if we move this thing away and remove any reflecting objects from the vicinity of the antenna under test, this is very important to be able to characterize the antenna polar pattern to its actual behavior. We have to remove any reflecting objects from the vicinity of the antenna, so we can say that the antenna has to be mounted roughly between the center of the ceiling and the floor. That's roughly about 5 feet or 4 feet from the floor, and any reflecting objects, specifically metallic objects, have to be kept as far from the instrument as possible. Now we can see that these log periodic antennas are having a gain of roughly about 4 dBs, and upon radiation of 90 dB microvolts of power from one of the antennas, we are able to receive a signal strength of roughly 47 dB microvolts by the use of these log periodic antennas. Now we change the log periodic antenna from a gain of 4 dB to the actual phased array antenna under test. Now we need to understand that right now this is a vertical polarization as of now, so the received signal strength is less. Without changing the distance, I'll bring the antenna in line and rotate the plane of polarization of the antenna under test. Now you observe that upon keeping the antenna, both the antennas in the vertical plane, right now this antenna is pointing towards the center of this antenna system, and you can see that your gain is 47 dB microvolts. We can change the plane of polarization to observe this thing in the E plane. This particular phase antenna right now will give a fan shaped beam. The beam is broad in this plane as it is mounted in the vertical mode right now, because the array has 2 antennas in the horizontal plane and 4 antennas in the vertical plane. So the beam is spread in the horizontal direction and it is compressed in the vertical direction. We are having connectors at the base of the antenna which allow the rotation of the antenna in its E and H plane modes to be able to plot the antenna in its electric as well as magnetic fields of polarization. Now we'll try to connect the antenna in its horizontal plane and show you the plot. The plot can then be compared with the simulated results of the phased array controller. We understand that if we give an incremental phase shift of 30 degrees to each of these patch antennas, what that means is that if this particular antenna is fed with a phase of 0 degrees, this one with a phase of 30 degrees, this one with a phase of 60 degrees, this one with a phase of 90 degrees. For the corresponding phase shifts, the corresponding DC voltages can be set from the controller and be read off from the table on the top of the equipment. That would result in the beam steering of roughly 7.5 degrees. So for 30 degree incremental phase shift, we have simulated the same thing in the antenna array software as well. The incremental phase shift of 30 degree will give us a beam steering of 7.5 degrees in the vertical plane right now. So to observe the beam steering in the vertical plane, we'll mount the antenna in the other plane to be able to clearly observe the beam steering, because we are able to rotate the antenna in its azimuth plane only. We come back.